Well, maybe we can start. I was asked to chair this panel. I'm not sure who's officially on the panel or not. But let me start the following way. I think we've heard today an amazing set of experimental talks. And if they have any reality, then this is going to be an amazing few decades in front of us to pursue gravitational waves and related fields that were talked about today. I'd like to probe the reality a little bit and at least what's involved in that. And so I'd actually like to ask the speakers who are here and will speak up to maybe reflect in the following way, to project yourself a decade or maybe more in some of these cases in the future to what you've talked about. And tell us what you would hope if you were invited to give this conference, but it was 10 years or so away from now, what you'd hope to be able to report to us. And what are the obstacles and what are the challenges to get there over the next decade? We saw some schedules, but I know that when we talk about getting there, there's both financial issues. We've heard that recently that ET was endorsed by Esri, which is a scientific endorsement, but in that we heard it cost 1.9 billion euros. I don't know how much of a challenge that'll be, but it's not simple where that'll come from. I know for LISA, we still need an official NASA commitment to join LISA. These are just things that I know about in terms of CMBS4, which we just heard about a few minutes ago. It involves unnatural DOE and NSF collaboration because of the scale of it. And so far, those don't exist, certainly on the NSF side, and just the first steps on the DOE side. Those are just the financial ones. I think at least as interesting is the technical challenges. I mean, I think most of us who have been around a while, like myself, have seen how we've been able to move forward in our science because of the technological developments. To what extent are we projecting technological development? Certainly in the atom interferometers, that's a case, but in other ones, for example, in gravitational waves, big challenge is to become cryogenic. And there's a big gains to be made there, yet it's very difficult. So I think it's worth each of you just reflecting for us a little bit, what are the big challenges, whether they're mundane like money or interesting like technology, and where you think you'd be, and to be able to talk about if you were invited to this meeting a decade or so from now. And I don't know who's still on that can do that. But
yeah, I don't know who you intend to go first. I mean,
yeah, well, we can start from the morning, maybe.
Yeah.
So maybe Salvatore was first.
Yes. Okay. So thanks, Barry. I mean, thanks relatively because it's a very hard question. Right. So I think compared probably to other designs and concepts which we have heard about, in the case of the Cosmic Explorer, at least at the zeroth order, I think the main issues are not on the R&D side, and of course that doesn't mean that all the problems are solved, but we do have a plan to start the Cosmic Explorer without Voyager-like cryogenics, right? Which would, of course, make it slightly less sensitive, but you still win a lot because of the length of the arm. Now, of course, there are still problems to be solved. Control, waveform control, high power operation. The mirror is going to be 300 plus kilos, and you need to keep that in place. And more than I can talk about, given my expertise not being on the instrument. So I don't want to give the idea that there are no challenges, but there is nothing that seems dramatic, at least from my perspective. Now, where the problems or the challenge, at least in my personal opinion, is getting the money, because like ET, it's a device that will cost more than $1 billion, and it's not easy to get that the money from NSF only. Right? Actually, I feel a bit bad telling this when you are chairing, because of course you have been and done this. And
well, let me since this is something I'm close to, I'll pick up on it a little bit. I would say there is a technological challenge. It's more mundane than cooling, which is a complicated one because we don't know what the right temperature to go to, what the right material is for mirrors, how to coat them, and so forth. So that's an interesting technical problem for the future. And as you say, we can skirt that and not be cryogenic at the beginning. But there is another technical challenge. It's much more mundane, but it's the fact that to go from, let's say, 4 kilometers to 40 kilometers, the vacuum system is 10 times as big. The vacuum system for LIGO was about a quarter of the cost of LIGO, which makes the vacuum system now become by far the dominant cost in a new generation experiment, unless we learn how to make a high vacuum system that is much less expensive. And that kind of work is really needed. And actually, we're starting to collaborate with CERN on that.
Right.
And others, but there are technological challenges which reflect, in this case, in money, and it's an engineering challenge.
Yeah, thank you very for pointing. Yeah, I'm aware that there are a lot of people thinking about the vacuum for next generation, and end of the collaboration, actually meetings which have already happened with CERN and workshops. Yeah, absolutely. Thank you for pointing that out. Again, I didn't want to give the impression that we know to do everything. And by we, I mean instrument person that actually will make that work. In terms of timeline, maybe I can say very quickly. So as I mentioned, the first step for us was getting this award from NSF to write the Horizon document, and we are delivering this now in 2021. After that, a while ago, the program officer for Gravity, Pedro Maronetti, gave us a tentative possible timeline. And the next steps are, some form of enthusiastic endorsement from the community on this Horizon study, right? Because when something is so expensive, you need to show that there is a very large base of users that will do science with it. And then the next step may be putting together an NRC report based on the outcome of this, and escalate that all the way up. So as I mentioned earlier, I think we're talking of another 9 years maybe from now, if everything goes smoothly, just to have some form of appropriation of the money or something, maybe 9-10 years, something like that. But again, that it assumes that everything goes right, which probably it's a bit optimistic. So if you invite me in 10 years, what I hope I can say is that we are about to either start construction or something like that.
Yeah, and I guess one thing that would be nice is to make sure that, or try to have a design and an implementation that works during the LISA active lifespan.
I think that's a great point. Thank you again, Barry, because we have heard from Antoine earlier about multi-banding, and once you do the math for LISA going to its operating point, plus the sources to go from the LISA band to the LIGO band, you want ground-based detectors to be online in the second half of the 2030s. And so hopefully we'll be there. I agree with you, it's something to keep an eye on, absolutely. It would be a tremendous waste of opportunity if we weren't.
Yeah, the other thing that maybe let me ask you to comment on is the need scientifically and the problem experimentally in developing a next generation network that has multiple interferometers.
Yeah, absolutely. So I think it's probably possible going to be even more important than it is for current generation detector, because right now we really mainly care about having a network for sky localization, so for EM follow-up, and to understand what's real and what's an instrumental artifact. In the next generation detector, there will be all of those still be true, but on top of that, to even measure the masses of high redshift objects, we'll need a network, because as I mentioned yesterday, what we measure here is not the astrophysical masses, but is 1 plus the redshift time the masses. So you want to undo the 1 plus z term. And to do that, you need to measure both polarization of the gravitational wave to measure the distance, and that requires a network. So even for intrinsic measurements of masses, it will be very important to have a network of 3G detectors.
Which compounds the problem of how ambitious to be, how expensive to be, and to be realistic.
Yeah. Exactly. And maybe, so again, it's worth stressing that because the network is so paramount for 3G, there is international organizations like GWIC and GWAC, of course, which are trying to think about this thing in a global way and be sure we end up with roughly at the same time more than one site.
Okay, is Sato still on? Or anybody else? The reality of a mid-band space experiment is unclear, at least to me. There's a lot of proposals, including Sato, including the Japanese, and in China. But I don't know what's the reality of any of these. Does anybody know anything? I don't see Sato here, but we've heard some reasons in this conference of why it would be nice to cover that band, but I'm not sure we know how real that is. Does anybody have any knowledge that the Chinese, I know, have 2 proposals. It isn't clear to me how real they are, or even how it'll be decided if they decide between them, because there's less history of kind of competitive proposals being decided by somebody in China. It's usually pretty top down. So there is kind of a LISA-like initiative to make something much more like LISA. And there is a mid-band initiative. They're separate groups. I don't know how those decisions will be made. So I don't know. Anyway, that's the gravitational wave part.
Maybe I can make a comment here.
Sure.
It's related to the recent ESA recommendations for Voyage 2015, who came out not too long ago, some 2 weeks or something like that. In that context, there were 3 science areas being proposed they would like to pursue for L missions, so large missions. And one of the science areas would potentially fit quite well a gravitational wave experiment with a potential focus on the mid-frequency band. There's no specification about technology. There's no specification about actual mission proposals or anything, but one of the 3 science areas recommended to be pursued for an L mission could potentially fit quite well that profile. I personally see this encouraging.
Yeah, that sounds encouraging. Okay, anybody else know anything?
So can you hear me?
Yeah.
Yeah. So not wanting to dampen Oliver's enthusiasm, and we talk regularly, so so it is indeed true that the sort of, if you like, the science side of ESA pushed for something which could accommodate what we would like to do in the mid-frequency band. But the administration of ESA historically has been somewhat skeptical about cold atom technologies in space. And they seem to maintain the skepticism to some extent. So there may well be a bureaucratic problem there, that of resistance that we need to overcome.
Right. But John, just to be clear, I was not mentioning cold atom technology here in particular. I was just mentioning that there's a science area that could fit a potential gravitational wave experiment in the mid-frequency band, independent of whatever choice of technology you would like to do.
Yeah, that's what I thought you said.
Yeah.
Anybody else have a comment about that? So let me go to pulsar timing. We still have, how realistic is that in a decade that we're going to actually see gravitational waves from pulsar timing? And we've had that promise now for the last, every year it's 5 years away.
Yeah, I can try to respond to that. Thanks.
I wasn't doing it as a challenge, but just so we really understand what the challenges are and what the expectations are.
I mean, the challenges have
You kind of did it in your talk, but maybe it's a little more informal here.
Sure. No, I mean, we had this promise. As I said, the experiments are spanning back 25 years. But if you look at the amount of sources that we can look at, that's driven both by the discovery of new suitable millisecond pulsars, by the ability to do multi-frequency observations to remove the interstellar medium, and by just the sheer sensitivity that we now gain with more and larger telescopes, I think it all plays in the right direction. I think it has been optimistic in the past. I think if the people would have known the challenges lying ahead of them, they probably would have been more cautious in starting, certainly more cautious in stating claims of when a detection is possible. But it's also fair to say that whenever we had more precision, more sensitivity, you kind of uncovered a new layer of systematic effects that you have to deal with. But I think now with our understanding of what the effects are, and this may not be completely complete, but certainly by our better understanding how important the interstellar medium and by how important things like solar system ephemeриdes are, I think we are very close of having a detection. But this is just a detection. I think what we really want to do long term is also use the signal that we see to actually do something about the physics, do something about the sources. That by itself is still, I think, quite a long way away. But the important thing about to recognize, and I didn't actually explicitly say that, in PTAs, the way we discover or detect the source is still quite different than what anything of the other detectors does. It's not just like we have a single event. It's a slow increase in the signal to noise ratio as time goes by. So even if we have a hint of a signal, the question is not really is it a signal? It's when do we declare we believe it is a signal? And so that needs certain tests. But my personal interest is really the physics behind it. I really want to have that sensitivity that we can measure the Hellingsson-Down curve and measure deviations from the Hellingsson-Down curve. That is still at least 10 years away, I would say. Maybe I'm pessimistic there if you ask other people, but having a detection, I think that's not too far away. Certainly in 10 years we will have a signal detected, but I suspect it's just a stochastic background. What we really like to see is single sources plus the Hellingsson-Down curve. And the single sources, you may just be lucky. I mean, it's not that the chance is not there to see something already, but the probability is low, but the probability to see a single source will increase with sensitivity. I didn't have a chance to talk about that in some detail, but that is certainly the case.
Let me ask you a question kind of as an outsider. Are we making the best use of the radio telescope facilities in the world. There's an American collaboration, there's a European collaboration, the Australians do something else, and then we have this huge thing in China called FAST.
Yep.
Are we hurting ourselves by having these independent groups? I know there's an international thing, but can you at least respond? Are we making the best use of what tools that we have to attack this?
Well, I think the answer will depend on who you ask. I can give you my frank answer.
Yeah.
I think we in Europe have in 2016 already proposed to everyone in the world to abandon all the regional efforts and just get together and just concentrate all our resources in pulling all our data together from all telescopes and really not try to sort of pursue independent efforts, but really have a joint concentrated effort with all the resources that we can put together. We believe in Europe, this is the way to go, because we already are sort of a mini IPTA in Europe. We already have 5 telescopes, and I think we work together extremely well. And we would have hoped that the North American colleagues and the Australian colleagues, and now also our Chinese and Indian and South African colleagues would go the same way. I think ultimately we have to do this. There's no question around this. And then we can time the sources much more frequent. We can coordinate the observations. And as you say, we can use the resources that are available in a much more efficient way. I think we are wasting a bit of resources here because of regional interests, because of funding constraints, there promises that were made in the past. But I truly believe this future is in a truly international collaboration. I think LIGO and Virgo have shown how it works, and we should just follow their example.
Yeah, we're independent collaborations, but yeah, we have a collaboration of collaborations that works very well.
Yeah.
Yeah, and that's maybe a model. What about the technology? Is there anything involved to make FAST part of, I mean, we've lost our Arecibo, but to get FAST into it, is there any technological issues in doing that? Do you know?
No, we are on the way. I mean, I myself work very closely with the Chinese colleagues. So we have in particular a collaboration with Max Planck and the Chinese Academy of Science just to work on this. And they are only a small step away from officially joining the International Pulsar Timing Race. So that is actually ongoing. And if you then know that, I don't know how well that is distributed, they have approved funding for 5 further FAST telescopes. So we better get them involved, because that is a tremendous resource to build 5 more of these things. I mean, the data will eventually dominate the PTA, I would say. But that doesn't mean that the other telescopes are not needed anymore, because we look at very long wavelengths, very long periods. So the baseline going backwards in time is absolutely crucial too. And that's why even if you have tomorrow the best telescope in the world, it doesn't buy you the detection. You really have to go back and look at the data in the past. But no, China will join. They're committed to join. It's just a matter of time. And I think the time scale is actually very short.
Oh, that's encouraging.
Yep. And then, of course, you have the SKA coming up. And MeerKAT is, I don't know, it's just such a tremendous improvement over Parkes sensitivity in the Southern Hemisphere. I mean, it's truly awesome, the data we get with MeerKAT. It blows us away whenever we look at it. And this is just a precursor of the SKA. So I think knowing that the SKA...
what's the realistic time scale on that?
Of MeerKAT is already running, right?
Yeah.
So we already have timing data for at least 2 years. And it's more sensitive than a GBT. It's more sensitive than Effelsberg. It's 7 times more sensitive than Parkes. And for the SKA, the funding construction has been given. Now the question is how fast they can put the more dishes together. Our institute, the Max Planck Society, is extending MeerKAT to MeerKAT Plus with additional 16 more dishes. And so that they're already slightly larger than the original meerkat dishes. That will improve the sensitivity by meerkat by another 50%. And the SKA will build on top of that. So I think within our meerkat extension will happen on a time scale of about 3 years. And the SKA will hopefully say 3 years later. So before the end of the decade, we will have a much more significant collecting power that will actually not be as big as fast, don't have to be honest. Will be more flexible though. And so the combination of both will be a game changer, I think.
Great. Okay. Raphael, can I ask you to tell us
Yeah.
the steps to get this thing official? I mean, through the DOE, the NSF, and so forth. So, I mean, what's the realism, the hurdles, and so forth?
So we want to start with the funding. So for the funding, I think you described the situation correctly. So CMBS4 is now an official DOE project, and there's DOE support. Obviously, not yet at the level that it takes to really build S4, but we're also not ready to build right now. So the hurdle, I guess, right now is still that we're waiting for the output from the decadal panel, which will influence what the NSF decides to do. Obviously, we're hoping that this all goes well, and then we get support from NSF Astro, NSF Physics, NSF Polar programs. But I think that's what we're currently waiting to hear. I think the DOE, as far as I can tell, seems committed to going forward with CMBS4. And what we were told is that we cannot just, if the NSF doesn't come through, what we cannot do is just downsize everything. So whatever we decide to do in that case still has to produce S4 level science with the amount of funds that we have available from the DOE. And so I think the most likely scenario would be that in that case, only the south pole of the primordial gravitational wave search goes forward, and the large, the wide survey from Chile would not happen. I hope it doesn't come to any decision making like that, because I think there's really a lot of exciting science. But it seems to me that even in an outcome that is bad, there will still be S4 level primordial gravitational wave science, which I think would still be something, but wouldn't be what we hope for, obviously. So I think that's roughly the
situation,
the current situation. There are smaller amounts of funding that the current stage 3 experiments were hoping to get, and so far that has worked, which I think is an encouraging sign, because I think if you were to give up on them, maybe you're also not funding the development that's needed later for CMBS4, but I don't know, it's hard to read, and I think we'll have to wait what the decadal panel says for the funding. You may have more insight into that than I do.
Well, I would say one thing you didn't mention that's a very positive step from my experience is that the DOE actually has made the step of determining a lead lab.
Lead lab, yeah.
And
so
that's
LBL.
That's Berkeley, LBL.
Yeah.
More important than that it's Berkeley, it's that they actually took that step, because that means all the things involved in making a project have a home and a place that does that, and it's necessary, whether it's safety or infrastructure or just all the things that we don't like to worry about, but the labs worry about.
Yeah, so that's what I mean, that the DOE seems committed, and I think
NSF's problem is a little bit different. I'll just give you my picture of what I think.
Yeah,
they've been running for many years on the big projects being funded through a special line in Congress, which is called Major Research Equipment Facilities, MREFC.
Yeah.
And the problem is that line has a more or less, because it's a line that goes to Congress, they don't like to change. Congress doesn't like to see big changes. They'll change 5 or 10%, but not factors of 2. And the problem is that that line in time has gotten both saturated and too small, because they haven't changed it very much. And there's more movement toward large projects just in general. So it's a problem of I don't think NSFs will. It's a problem of basically the one place where they put it being oversaturated at the present time. The last director of the NSF tried to, before she left, tried to increase that budget, double it. And that didn't happen during her reign. I don't know the present director well enough to know how hard he's pushing that. He says the right words, but he comes from a different background. So
Okay.
I don't know. There is in the present budgets that are a very large increase if it survives for the NSF. If that happens, I would hope that they manage to increase the amount in this MREFC. I don't think Goodwill is going to support CMBS4.
Oh no, yeah, sure.
It's going to require an increase in that line that's very visible in Congress. But it may be that it can happen this year because the NSF may get a large increase. The competing thing, unfortunately, is that a lot of the support in Congress is to do more practical things, technology development.
Technology, yeah.
Yeah, so we have to see, and I hope somebody's pushing hard for you guys. But there is an uncertainty there, I think.
Yeah. Yeah, and then you're also asking about technology, so I can say some words about technology, but I want to just remind people before I do that I'm really a theorist, so I'll do my best. But so I think what is good for S4 is that it can really use a lot of the things that are already being developed for the experiments that are happening or about to happen. So for example, the LAD telescope design will be the same as for Simon's Observatory and CCAT Prime, but it will have significantly more detectors in the focal plane. The technology of the detectors that will be used is also the same as what is currently being used. So these are transition edge sensors, which really have been tested. And I think there's no big worry about the detectors themselves. The big challenge is because there are so many more detectors and one has to read them out without changing the temperature. So there's a lot of work on the readout. So this is one of the biggest risk factors, I think, and the main strategy is really to develop different technologies, different readout technologies, and test them in the upcoming experiments. For the detectors, I guess one also has to demonstrate that one can actually mass produce them, because right now they're kind of produced in small quantities, and for CMB by universities, or then by Argonne for SPT, but this really needs to be scaled up dramatically, and that really hasn't been demonstrated. But the hope is that this can all work, but that's something that needs to still be demonstrated. For data management, I think, or the simulations right now, just based on the size of supercomputers or the time we can get on them, we can't really simulate the full instrument. So we can only simulate small, short periods of time with a subset of the detectors. Eventually, I think one would want to be able to simulate the full instrument, which right now we cannot. So there, I guess, we're still assuming that Moore's law will hold for a while longer, and we actually get to run the full simulations for the full instrument. There are some things that still have to be developed for the optics, like the anti-reflection coatings, but there's still a lot of work for the cryostats, because they're significantly bigger and more involved. There's also ongoing work, but I think there it's helpful that the same telescopes for the LADs at least are used for SO and CCAT Prime. So I think one will learn a fair amount from the ongoing set of experiments. The ground pickup is still being developed. So there are still a lot of things, but as far as I can tell from talking to the people who actually do this work, they don't think there are any showstoppers. So I think the feeling is that this is something that can all work if one really gets to use, if the current set of experiments goes forward. And I think part of, or one advantage here maybe, is that at least for SO, one isn't so much dependent on federal funding, because it's supported by Jim Simons. And so at least that one will go ahead. I mean, we know that the funding for that is there. And so those aspects, I think that it has as I said, the same hybrid structure with large aperture telescopes and a small aperture telescope. So a lot of the technology will already be tested. So it's then a question of whether one can scale it up. And that needs to be demonstrated and is actively being worked on. But so that's roughly the status, I think, for the technology.
In terms of the simulations which you referred to, what is it about the problem that makes it so demanding?
Oh, it's just a lot of detectors at the end of the day. So you have 500,000 detectors that you would like to simulate data for simultaneously. It depends on what you're trying to simulate. So we do simulations at different levels. You can do map level simulations for the full instrument very easily. So we can easily simulate the maps and analyze them. This is what the forecasts are based on. So we do map-based simulations. Eventually, you want to really take the instrument and make synthetic observations of the sky. You want there to be a model of the atmosphere that you're looking through. You want there to be a sky model and a CMB, and you're really trying to produce the time order data. And if you're trying to make maps with 500,000 detectors, then that's just challenging. So what the largest simulations, I think, that have been done for tens of thousands of detectors for a week. This takes the full NERSC Cori supercomputer, and so it really I think you don't have to simulate the full 7 years. I think that is not something that one has to do, but at least some reasonable time period for the full instrument, I think, is something one would want to be able to simulate to make sure one can use the data as planned.
And do you need that before you actually implement it, or by the time you finish it?
I think by the time you finish it, also because you want to then, I mean, for example, if you look at how the Planck data analysis worked, I mean, you may find that there are some systematics in the data that you didn't anticipate when you built it, and you may have to model them with a simulation. So by the time you want to analyze the data, I think you want to have all that in place. Right now, I think it's not critical yet.
Yeah.
But I mean, for example, the only reason Planck was eventually able to measure the optical depth is because they really simulated the issues with the analog to digital converters, had detailed simulations of the instrument and tried to remove all of that. And I mean, maybe one will not need it. Maybe the data is so clean, but I think one can't be sure of something like this.
Right.
Yeah. And so.
Okay.
For the conference, I guess. Well, you asked about the conference in a decade from now. And so I don't know. So the current plan is that the construction starts in 2028. So a decade from now, I guess one has 2 or 3 years of data, but they're at that point not analyzed. So maybe what one should do is have the first year of data and analyze that, so one can present that at a conference a decade from now. It would be competitive with a stage 3 experiments, and so I think that's an interesting thing to try and do. So that's something one could hopefully present in a conference a decade from now, but not the full results won't be available a decade from now.
And that also assumes that you get the funding and it works on the time
that
scale.
assumes that we get the funding.
Yeah.
And I put 1 year in for delay, but it could easily be longer. So.
Right. Okay, thanks.
Yeah.
Oliver, how do we get going on atom interferometry in some way that we can convince people like the European Space Agency or anybody else that this is a direction of the future? I mean, you guys are worrying about how to attack the physics in the long term, but what are you doing in the short term to get some confidence that this is a technology that we should pursue, that people who are skeptical can realize it's something that we need to pursue? So how is that into the plans, or how can?
Well, that's certainly the most important question when it comes to the use of quantum technology for fundamental physics. It's, from all the technologies we're probably looking at today, the most uncertain one in terms of its readiness for doing the fundamental physics. But I think the positive aspect is here that in the last 4 to 5 years, there were a lot of interesting developments in that community related also to funding scenarios. If you look, for example, at the UK, we were able in the last 2 years to secure around 40 million for quantum technology development for fundamental physics. This was completely new money, which was given to the community. And out of that 40 million, ION has around 8 to 9 to start developing the prototypes we would need in order to demonstrate to the rest of the world that this atom interferometry can work up to the expectation. So for example, in the UK, we're building now in Cambridge, in Oxford, in Birmingham, at Imperial College, but also at RAL, 5 independent laboratories, each of them 2 million, to push the technology in 5 different directions. So these are essentially 5 basic parameters we would need to develop to a higher level of understanding to show that this atom interferometry can work. In parallel, there's a lot of other interesting activities ongoing, for example, in the US, as you might know. The US even has, as we speak. It's currently in construction, if you like. It will not have the same specifications we need in order to go for gravitational wave physics, but it would start to serve really as an important prototype version to show that we could, in a staged plan, reach the sensitivity in a decade or even 1.5 decades from now for gravitational wave physics. So I think this is also encouraging. Plus,
and how do you understand the time scale for that one?
For the 100-meter detector and matches, I mean, they're building it right now. So the 2 atom interferometers, which will be built, actually, they will have 3, but let's start with 2. They are under constructions. The sidearms, as we call them, are almost ready, and installation in the minus shaft at Fermilab has started. Yeah. So the expectation is that experiment is built to its first specification in around 1.5 years from now, and then we'll start data taking. It will not start data taking immediately with the sensitivity you would need to get gravitational waves, but it would already be a first prototype version to demonstrate the technology.
Yeah, which is needed because
yes,
it's new enough that somehow there has to be confidence in the community first, and then in the agencies, I think.
And as you might know, we have partnered with the US now. The UK has partnered with the US,
which is
so
good.
we are actually making a 2 million contribution to matches from the UK, and we in parallel in the UK will further develop the technology. So you will have a 100-meter experiment built under realistic conditions with parameters which maybe not be the ultimate state of the art, but in parallel, in that 2.5 years of that program, we will develop further the technology in the UK in the laboratory so that it can be then deployed also to this 100-meter detector. So I think we do have a plan forward, but obviously it's a high risk, high gain endeavor. We all know that. I mean, there's several open knobs and things we will have to prove, but money is available right now. People are willing to commit their time. I think this is also very important. So we got really all the big experts in cold atom technology committing to that program in the UK and in the US. And I think already by 2025 or 2026, we will know much more.
Yeah, great. Okay. Anybody else? We lost a bunch of speakers, so I can't address them. But anything anybody wants to throw in? We've got a couple more minutes.
Well, maybe John, if you want to add something. John Ellis is also quite heavily
Sure.
involved in the
I know.
program. John?
Well, yeah, I don't think I have anything more to add to what you said about AON Edge and cold atom technology. I think it's interesting to think what one can do in the gap between pulsar timing arrays and LISA, which looks like it would be very interesting. So I don't know whether we have time to discuss that. We heard some ideas earlier on using asteroids, which sounds a bit futuristic, but okay, let's think about that. I'd actually also be interested to know from Michael Kramer why he's so optimistic that you'll see a gravitational wave signal soon. I understand what the power law would be in astrophysical sources, but how about the normalization? How confident are you about that?
Yeah, the amplitude is, of course, very interesting from an astrophysical point of view, because it would tell us a lot about the formation and merge of galaxies. So there have been there have been publications by Nanograph and the Barks Pulsar Time Array in the past, which put up upper limits which are well below the kind of signal that we see right now. And you can ask the question, what has been done there? But I think the level we would see now, if it's a real signal, it is consistent with what has been sort of expected based on astrophysical arguments in the past. So the amplitude itself has the right order of magnitude. And as I said, the signal builds up slowly. And we have seen a hint of the signal earlier. It's building up. So that gives us maybe some confidence that it's real, but I would still caution. But I'm just optimistic because given the fact all the advances that we have made in the last couple of years, 5 years, 10 years, I think means that we're really nearing the detection. But as I said, it's not a detection like with other detectors that you can see signal that you follow. It's really a slow buildup of the stochastic amplitude in signal to noise. So it would be really nice to see single sources. That is, as I said, still quite some time away.
So, Michael, if you project on the future, since you know the scaling of your signal to noise ratio with time, how far do you think you are from going from this? Maybe we saw something to 3 sigma or 5 sigma. We saw something for the stochastic part.
For the stochastic background, I think we now have put out preliminary papers. So we are out to put out preliminary papers. We are now analyzing a much bigger sample, longer data set. For instance, EPTA, the results I showed you was based on the 6 best pulsars. We're working on more than 25 pulsars right now. So if you scale it up, we should be above 3 sigma maybe by next year, if the signal is real, which again, I caution, may not be the case. Yeah.
Okay, any final comments anyone wants to make before we close?
Maybe I can add a
Sure.
few words about about LISA. In terms of I don't know if my sound is okay. Can you hear me?
Yes, yes.
Okay.
Yes.
So about LISA, I think we are in a good shape in terms of technology because we don't have showstopper. The main difficulty in terms of technology is we have to build these 3 spacecraft with these 6 MOSA, and to align this everything with a very good precision. So it's more on this side, but in terms of pure technology, we don't have any showstopper. In terms of funding from the European side is quite consolidated. We could have some delay because of delay of other mission. LISA is in a good shape and the planning is quite solid. But in terms of funding, we have there is also Athena that is a big mission for ESA, and if Athena has already 6 years of delay and to be at the launch start to be at the same time as LISA, so it's maybe a bit complicated for ESA to launch the 2 missions at the same time, but except on that, we're in a quite good shape. But so we hope to have some nice result by 2036, 2037. It was just to add a comment about LISA. I think we are quite okay on this side.
Good, thank you. Okay.
Can I say a couple of words about this high frequency
Yes, please.
initiative that we have launched? So it's hard to single out a single technology challenge because we are still in a preliminary stage in which we want to decide what's the best technology to be used in the various frequency ranges. But there are different situations. So for instance, there are some projects that are already well underway. So for instance, in this around the 100 kilohertz, there is this optically levitated sensors that is already partially funded. They are building a prototype that costed like $1 million US dollars. And so for this kind of experiments, the goal is to get the next round of fundings to scale up the experiment and go down in sensitivity. Then there is a need for some of these isolated attempts that there have been around, like the bulk acoustic wave devices and even the optically levitated sensors, to build larger collaborations that focus on single technologies. We have had, I mean, we got some requests in this sense, whether we could help these collaborations. I'm thinking that maybe one could try to build something like what has been done with MADMAX or ADMX for axion experiments. You know, to use more efficiently the resources and share knowledge for a single technology. Then in other cases, there is an overlap with the axion experiments. So one can think of a double use of these experiments. And probably there is DESY that has some knowledge in this direction that probably would like to invest some time and money on this. And then last thing is that it would be nice in say 5-year time to start the testing phase for some of these proposals that are only theoretical at the moment. So this is the situation.
Thank you. Anybody else want a final word? Okay, if not, I'll call this to a close. I have to prepare a talk for a half hour from now. So I'll see some of you then.
Thanks. See you.
Okay, bye.
Bye.